Wow, what a beautiful sunset. I can't think of a better way to enjoy a sunset than solving a really nice comparametric equation. So, just gonna go up to the roof where I can see this beautiful sunset. That's really nice. Really beautiful sunset. And take my chalkboard here. And somewhere where I can enjoy this marvelous sunset. The nice thing about a small chalkboard is I can be anywhere. I can go to the beach. You see, with a remote classroom, your classroom's anywhere you want it to be. Right up here is quite nice. So this was our last lesson here. Now what we're going to do is enjoy this wonderful light here, this golden hour, just before sunset. And we're going to move from infinitesimal scaling, which was our lesson with Adnan, back to something really, really simple. One of my favorite comparametric equations, just because of its pure simplicity. It's a super simple comparametric equation. Really, really simple comparametric equation. And that is, let's take, let me stick of chalk here. I always keep a piece of chalk in my pocket. This is a Hagoromo, the world's best chalk. Now, let's take this example here, and we're going to solve g equals the square root of f squared plus 1. Very, very nice, simple comparametric equation. One of the reasons I like this comparametric equation is because it's easy to solve. It has no real practical use that I can think of in terms of photography or imaging, but it's sort of designed to be easy to solve and thus illustrate the concept of solving a comparametric equation. So we're going to begin by letting f of q0 equal f0. Now, therefore, that kind of gives us, f1 equals f of k q0, which equals square root of f0 squared plus 1. And we have f2 equals square root of f1 squared plus 1, which is equal to square root of f0 squared plus 1 under the square root sign squared again plus 1, which is equal to square root of f0 squared plus 2. And then now f3, we have f3 equals square root of f2 squared plus 1, which is equal to the square root of f0 squared plus 2 all squared plus 1 under the square root sign, which is equal to the square root of f0 squared plus 3. And so you can see there's a very simple pattern that emerges, that f to the n, fn, the nth f, is equal to the square root of f0 squared plus n. And now, the key to unlocking these comparametric equations is to recall or remember our sort of magic graph theory sort of thing. So recall that k raised to the exponent of n equals q over q0. That is kind of that magical thing that we remember. If you remember back when we did that graph, that sort of graph theory, remember how we had the photocell experiment. When we had the photocell experiment, we had something like this. We had some quantity of light q0, and then 2q0 when we were doing it with a 2-to-1 ratio, 4q0, 8q0. Remember when we were doing it with a 2-to-1 ratio, and it was something like this. And if we change this axis to instead of and this was q and this was f of q, remember we had that axis. Now the first thing to do is to sort of change this to q over q0, and then these become 1, 2, 4, and 8. And then more generally, for general value of k, instead of 1, 2, 4, and 8, this becomes 1, this becomes k, this becomes k squared, this becomes k cubed, and of course k is just k to the 1, and 1 is just k to the 0. So I'll just write that as k to the 0, k to the 1, k squared, k cubed. And so what you can see here is that k to the n, the general term along this axis, k to the n is just this thing, q over q0. And that is the key to unlocking comparametric equations. That's kind of the magic index key that sort of opens up the comparametric equation to a solution. So once you recognize that, then you've obviously got your key to unlocking the comparametric equations, or simply written in the other form that you would more readily use it as n equals log q minus log q0 over log k. So it's the logarithm of n is equal to the logarithm of q minus the logarithm of q0 over the logarithm of k. So now, so if we come down and use this key to unlock the comparametric equation as it is, and come into here, we have fn from here is equal to the square root of f0 squared plus n, which is just log q minus log q0 over log k under the square root sign. And of course, if we recognize immediately this is just a constant, like what we have more or less is, like we recognize there's a constant in here. What we have is that this is f0 squared plus log k of q minus log q0 over log k, and this is just log k of q0, so this is a constant. So what we really have is the square root of f0 squared, and minus this is a constant, and then the log k. So let's just I'll just go backwards, back up the chalkboard here. So this equals the square root. So let's let c equal f0 squared minus log q0 over log k, and then what we have is this thing f is equal to, or fn in general is just your function f. So Fn equals F, let's say, which is just the thing that we're trying to find or trying to solve for. And that is equal to the square root of log base k of q plus c. And so let's verify. So this is, we're saying now we've solved this comparametric equation, g equals square root of f squared plus 1, and the answer is f equals the square root of log k of q plus c. And let's just confirm or verify that that is a solution. So we'll verify that's a solution. So we're going to verify so we're going to say f equals square root of log kq plus c, and then over on this side we've got g equals square root of log kq plus c. And then we want the easiest way to bring or relate these together is going to consider, let's consider f squared equals log k of q plus c, and g squared equals log kq plus c. And then if we just sub them in together, if we just take this is equal to log k of k plus log k of q plus c. And we've got here that this is just equal to log k of q plus c plus 1. And so we have here that g equals plus or minus the square root of it's going to be the square root of this function. Okay, so let's verify that that's a solution. It's getting a little windy up here now that the sun's setting. I'm going to come back down in a few minutes, I think, because it's getting a little cold up here. But let's verify that this is a solution. F equals the square root of log k of q plus c, and likewise g equals the square root of log Okay, let's verify that this is a solution. So we have that f equals the square root of log k of q plus c on one side, and then over here we've got g equals the square root of log k of kq plus c. Now let's consider f squared equals log k of q plus c, and g squared equals log k of kq plus c. That's in brackets there. And then which equals g squared is equal to log k of k plus log k of q plus c. And what we have is if we recognize this log k of k plus c, that's equal to, we can just, I'll group them together, it's equal to log k of q plus log k of q plus c, and we can recognize that's the same as f squared plus log k of k, which is just equal to 1. So that is equal to f squared plus 1. G squared is equal to f squared plus 1, so therefore G equals plus or minus the square root of f squared plus 1. So we've verified, in fact, that we've solved the comparametric equation, and then we've verified that that is, in fact, a solution. So now we can feel wonderful that we've solved a comparametric equation just as the sun's setting on this beautiful city of Toronto. Marvelous. What a gorgeous day to solve a comparametric equation. So one of the nice things we learned from all of this, from this comparametric equation solving g equals square root of f squared plus 1, was a key sort of observation. Because it's such a simple comparametric equation, it gives us a chance to really understand quantograph theory. And so quantograph theory is this idea. It comes from the photocell experiment. You know, the quantograph theory is a way, kind of a philosophical way of looking at graphs. Like if we were to make some kind of quantity, typically you often have a table of entries. Like if you have, distance, or let's say you have the time that you allow, and then you have distance that you go in that length of time. So if you have, let's say you're going for a swim and you're going very slow, easy, just a nice steady pace, so you can maintain the same pace for a long time. Let's say we swim 50 meters in 1 minute or something, just a slow, gentle pace. So if the time is 1 minute, then we can swim, we'll swim 50 meters. And if we have 2 minutes, then we're going to swim 100 meters. And if we have, as you continue to increase the time, you'll have 20 minutes, and then you'll have 1 kilometer. The way to look at this quantigraphically, so the way to think quantigraphically is to change this to time divided by minutes, and change this to distance divided by meters. And then this becomes a truth table. This becomes a table of what's true in there. And then you just write the numbers in here. Now, it's not time in minutes, or it's not time. Sometimes people will write time bracket minute, or they'll write time in minutes. But these are wrong. That's wrong. That's wrong. What's correct is time divided by minute, because this is a truth table. A table is a truth table. Time divided by minute equals 1, at which point distance divided by meters is equal to 50. Time divided by minute equals 2 when distance divided by meters equals 100. Time divided by minute equals 20 when distance divided by meters equals 1,000. And so on. And if we were to draw a graph, speed equals, distance divided by time, meters per second. So a more right way to say that is, in terms of units, is speed divided by meters per second equals distance divided by meters over time divided by seconds. And then we can get that into quantograph theory and say if we had, let's say the slope is the speed, and say this is distance, and let's write this here as distance per meter. And if we write over here time per second, then we write those out. Distance per meter divided by time per second. So distance per meter is going to be, so you're gonna have a line here of a certain slope, and when the time is 1 minute, if it was by second, then this axis would be 60, and over here 60 seconds gives you 50 meters, and then 120 seconds gives you 100 meters, and so on. And these are just labeled, and a graph is just the locus of points for which something is true. So that's simple graph theory. A graph is the locus of points for which something is true. A table becomes a truth table, the table for which things are true. So I don't want to see distance in meters, or distance bracket meter, or distance dash meters. I want to see distance divided by meter. And I want to see time divided by second. And that philosophy, that's called quantigraphics. That way of thinking of the world, we call that quantigraphics in some way. Photoquantographic, there's this philosophy of comparametrics kind of can extend to general life. Quantigraphics. So if we had, going to our other example here, when we had this graph, when we had Q and F of Q, we had Q was Q0, Q1, Q2, which is, K Q0, let's say K squared Q0. And then we very quickly realized that if we simply change this axis to Q over Q0, then this axis becomes, K to the 0, K to the 1, K squared, K cubed, and so on. And that gave us this notion, it gave us this identity, K to the N equals Q over Q0. And that is what we use to kind of solve or unlock these comparometric equations. So that's a very important observation. It's very important when you think of things in this really clear way, it becomes super easy to understand things. And so this all comes from the photocell experiment. We have a certain amount of light and a certain proportion of the change in the gain of light. And as we adjust the amount of light, the photocell follows the path of the photocell in terms of its closeness to this light source, follows this trajectory. And so I've got here, we built a simple little experiment here. We kind of automated that photocell experiment. And what it does, in this case, it lights up 20 lights, and then it lights 21 lights in succession. And so there's a motor here, and it's motorized. So this photocell, it's completely automated, the experiment. All I have to do is sit here and watch it run. And what it does is each time it runs until it gets to the same amount, until it matches the amount of light. So you see here there is 20 lights, and then it turns one off and then moves it until it's the same as 21. So now it's got 21 lights lit, takes the value, and it's going to move it till it's the same as what 21 did, and it's going to do it over and over again. And you can hear the traces are getting shorter each time. So it's kind of logarithmically, roughly expanding. Now there's some room lights on here. This experiment should really be done in total darkness, so it's not terribly accurate at the moment, but you can see what's happening here. You can see it. 21 lights, and then 20 lights is equal to the same as 21, and it just keeps doing it over and over again. and gets shorter and shorter and shorter. These traces here, this distance that it travels is getting shorter and shorter and shorter. So you've got k equals 21 over 20 in this case. So you've got k equals 1 plus epsilon. So the epsilon equals 1 over 20th. And of course, when it's all finished, it'll go back and it'll start the experiment over again. See, it's running much longer for that first run until it matches. Eventually it'll slow down and it'll hit the point where it matches and it'll read out that value and so on, and it just continues to repeat. Unplug that 12-volt battery, and so you can see very importantly. So this the kind of the key observation is we've got this notion of k to the n equals q over q0, and therefore we have your n equals log q minus log q0 over log k. And so this is sort of this key concept in comparametrics that comes from quantographic theory. So let me take this very simple but important result here and just put it over here on the little sideboard here, which we can then use. And that is to say that n equals log q minus log q0 over log k, and maybe in a more convenient form we'll just simply write that n equals log base k of q minus log base k of q0. It's simpler maybe just to think of the logarithm as the base. So for example, if k equals 2, then we're doing everything log base 2. If k equals 1.01, then the base of the logarithm is 1.01, or maybe the base of the logarithm is 1 plus epsilon, or whatever the case may be. So I'll just set that aside for a minute now, and then let us grab another simple example of a comparametric equation that we can solve. So we'll take this right here, and we'll go, example 2, let's call this. So we're going to take an example 2, and we're going to solve, let's say we're going to solve, stand up for this a little bit here, solve g equals AF. In other words, this is the comparagraph, and it's just a straight line that passes through the origin, and the slope of the line is A. So now, let f of q0 equal f0. Therefore, f1 equals f of k q0. And again, we're kind of, applying this similar principle of kind of going around like this, and, just philosophically, that's so we're just kind of unrolling or unraveling this mystery here that we have. And so f1 is equal to f of k q0, and so that f1 equals a f0. This is just the iteration on this. F1 is assuming the role of g, and f0 is assuming the role of f, and we're just kind of iterating it again. And then f2 equals a f1, which equals to a times a of f0, which is equal to a squared f0. And then we have f3 equals a of f2, which equals to a times a squared of f0, which is a cubed of f0, and so on. And we'll have now that fn is equal to a to the n times f0. And so now here's where we make that substitution again. We're going to put in here, we're going to recall our relationship here. And now we're going to just simply substitute that in, the sort of quantigraphic principle here. And so therefore Fn equals a to the log base kq minus log base kq0 times f0. And so now we simply say, and that is equal to a to the log kq times a to the negative log kq0 times f0. So there's three terms here. And so now we can notice that this term here is a constant, and we'll call that, let's call that beta. And then now, if we just continue over here, let's see, we'll continue up here. And so now, we just continue over here, that now Fn, so let's just continue up here, and we have Fn is equal to Fn is equal to beta times a log k of q. Beta times a log k of q. And so that is equal to beta times q to the log k of a, which equals beta times q, and we'll introduce another letter. This is just a constant log k of a, so it's beta q to the gamma. So we have that f equals beta q to the gamma is a solution of the comparometric equation that we had before, g equals af. So this is solved to give us this here using this very simple principle. And we've used here the very simple principle that that a to the log q equals q to the log a, which applies for any base, i.e. a to the log base k of q equals q to the log base k of a. So we've simply substituted that in. Okay, let's consider a third example. So if g equals af plus b, where if this is f and this is g, we have a straight line of slope a and intercept b. And so we just want to solve that comparometric equation. So again, same thing. Let f of q0 equal f0, and therefore f1 equals f of kq0. Remember that f, the present f is forming the role of f, and the next f is forming the role of g. So again, f1 equals af0 plus b, let's say. This is kind of a iterative process. Remember, we're just going around this thing, unrolling it, just like before. And so F2 equals A times A F0 plus B, and that equals to A squared F0 plus B times A plus 1, and then F3 equals A cubed F0 plus B A squared plus A plus 1. And more generally, we can write that the F sub n equals A to the n F0 plus B times the sum from I equals 0 to n minus 1 of A to the I. So you can see this is just a simple pattern here, and that is equal to A to the n F0 plus B A to the n minus 1 over A minus 1. This is just the sum here. And so again, recall what our side, our little side result here, our comparametric result that we had here. N equals log k of q minus log k of q0. So we're just going to substitute that in as before. So we're going to substitute in here that f sub n equals a to the log kq minus log kq0 times f0. So we have here plus b times a to the log k q minus log kq0 minus 1 over a minus 1. So again, just this thing goes to here, and this thing goes to here under this substitution here. And so now that Fn, now you can see a pattern here. So this is, there's terms here. This has a term in Q. This depends on Q. And so this factor here is just a multiplicative constant. So I can kind of bring that out and say, okay, this is a to the log kq times a to the minus log kq0 f0, and you can see this is just a constant times a to the log k of q plus b times a to the log k of q a to the minus log k of q0 underneath a minus 1, and then I can multiply this out, and it's just minus b over a minus 1. And so you can see what we have here is these terms are all in a to the log k of q times some other constant, and so is this. So you can factor that out, and you can see that this is equal to some constant times some constant, say constant 1 times a to the log k of q plus some other constant 2, say this over here. So you can see And if we take what we had before, namely the logarithms, then that is equal to, you can see this is of the form, let choose for this constant beta, and this is q to the gamma, where this, we take this a to the log k of q is equal to q to the log k of a, and let log k of a equal gamma plus alpha. So we can see, more generally, we can write that f equals alpha plus beta q to the gamma is a solution of G equals AF plus B. So we've solved that simple comparametric equation again using the same fundamental principles. So we just keep in mind this fundamental principle which we learned from this simple sliding rail. All we started out with right at the very, very beginning, we started out with this very simple apparatus here, which is just a simple thing connected to a photocell. And that was kind of where it all started, as we started with this very, very simple apparatus. And, you know, just moving along. So we started unrolling that comparagraph. So we simply had some unit f of q and f of kq. So we have f of 1 plus epsilon times q versus f of q. And so again, we had one of the LEDs came on, and then we moved over until, turn it off and move over until it's the same, then turn the other one on, then turn it off and move it over until it's the same as it was when it's off. And we just iterate on that, and this gave us, again, that very, very fundamental iteration principle of n equals log kq minus log k of q0. And so we simply use that fundamental principle here to solve these equations. Thank you for watching.